Welcome to Unit 9 of Chemistry, Gas Laws. So let's take a look at how gases behave. In the late 19th century, scientists developed the kinetic molecular theory, which we abbreviate as KMT, to account for the behavior of atoms and molecules that make up matter. The kinetic molecular theory is based on the idea that particles of matter are always in motion. So as you can see here, solids, liquids, and gases are all made of particles in motion, although their amount of motion varies dramatically. Solid particles are very closely packed together, so they do move, but not very much, and their volume is fixed and shape as well. Liquid particles slide over each other. There's a little bit more space between them, and so they are able to change their shape based on the container that they're in, but their volume is generally pretty consistent. Gas particles move very freely and rapidly, and they expand to take up the volume of their container, and they are also able to change shape based on the shape of their container. And because their motion is so visible and there's such distance between those particles, scientists use this to develop the kinetic molecular theory a little bit more clearly. They focus on gases because their behavior of particles is so much clearer and easier to understand. So what are the assumptions of the kinetic molecular theory? It's based on 5 assumptions, and again, these are based on gases. They can relate to all of the other phases of matter as well, but we use them in reference to gases because the distance between the particles is so much greater. Gas particles are in constant random motion. The energy these particles have is known as kinetic energy, or the energy of motion. So they are constantly moving in a random direction. Gas particles are much smaller than the distance between the particles, so most of the volume of a gas is empty space. And you could see that on the previous diagram as well as here. These particles are much smaller than the distance between them, unlike a solid and sometimes a liquid. Gas particles experience elastic collisions, which means that there is no loss of energy. The energy is not absorbed when particles run into each other in a gas, that they are experiencing completely elastic collisions, not losing energy or gaining energy as they hit other particles. Gas particles do not attract nor repel other gas particles. And the average kinetic energy of a gas is proportional to the temperature of the gas. Now, these are assumptions that are based on an ideal gas. So these don't always occur in real life, but we do assume these to try to get to understand gases as closely as we can, even if it's not a perfect version of the motion of these particles. An increase in temperature causes the particles to gain energy and collide more frequently with each other and with the wall of the container, which causes the pressure of the gas to increase. So we often represent the motion of gas particles by arrows here, and these arrows are moving in random directions. As the temperature is increased for this gas, obviously these particles are not to scale, but you can see what happens to them a little bit more clearly. As the temperature increases, they are going to have more motion, so we make these arrows longer to represent that. They are moving faster and bumping into each other more frequently and into the walls of the container at a higher temperature here. So that's going to increase the pressure because pressure is based on the collisions with the walls of the container. These result in a predictable relationship between temperature, pressure, volume, and the quantity of a gas. So the first container here has a low temperature, causing few collisions and thus a lower pressure. And this container has a higher temperature and is going to have more collisions and therefore a greater pressure. It's also going to adjust the volume of the gas if that's flexible. And so we're going to, throughout this unit, look at all of the relationships between temperature, pressure, volume, and quantity of gas particles. What is the Kelvin scale? Well, as the temperature of a gas decreases, the particle movement slows down. So we were just talking about how an increase in temperature causes the particles to move faster. A decrease in temperature causes the particles to slow down. Absolute zero, which is negative 273 degrees Celsius, is the temperature where all particle movement stops. So this is a hypothetical temperature because we wouldn't be able to observe a temperature at which all motion stops because you wouldn't be able to see anything. You wouldn't be alive. Particles wouldn't be moving in your body as well as anything you were looking at. So this is a theoretical temperature, but we do consider absolute zero where all particle movement stops. And the Kelvin scale is the one that we use when we are measuring gases because the zero in 0 Kelvin or absolute zero means there's no particle kinetic energy. So that helps us to remove a variable sometimes when we are discussing particle movement of gases. So whenever you're doing problems throughout this unit, rather than using Celsius or Fahrenheit, we're going to be using Kelvin. And in order to calculate that, Kelvin is the degrees Celsius plus 273. In summary, the kinetic molecular theory predicts the behavior of gases based on a few assumptions about their size, motion, and energy. The kinetic energy of a gas can affect its pressure, except at absolute zero, where there is no particle motion. So we've been loosely discussing pressure so far, but what exactly is pressure? The states of matter behave differently when pressure is applied to them. So we've discussed the kinetic molecular theory and how it relates to gases, but all the states of matter behave differently when pressure is applied to them. It's just that the gases have the most space between the particles. And so when pressure is applied to them, they are able to change significantly. Pressure is simply the force per unit of area. The SI unit for pressure is the Pascal, which is equal to 1 Newton of force, so Newton is a measurement of force, per square meter of space. So we're talking about force over a certain area. Molecules of air move in every direction, exerting force or pressure on objects within the air. So we call this atmospheric pressure or air pressure sometimes, because the molecules of air are exerting force on objects around them, including people or items within that air. The average air pressure at sea level is 101.3 kilopascals when the air is at 0 degrees Celsius. This is known as 1 atmosphere. So we make this just a common measurement of pressure. Even though the SI units are pascals, we often use atmospheres. And as you can see in this illustration, atmospheric pressure is higher at sea level because there are more air molecules actually pressing down on anything at that sea level. As you get up in elevation, there is lower air pressure, and that's sometimes why you need to bake things differently if you live at high elevation, and why it's important that we designate sea level when we're talking about atmosphere, because the air pressure is different at different elevations. What is Dalton's law of partial pressures? When Dalton was experimenting with gases, he found that a combination of gases exerts a pressure equal to the sum of both individual gas pressures. So if we have a gas at one pressure, for example, 300 pascals, and we combine that with a gas at a different pressure, let's say 600 pascals, the combination of the gases exerts a pressure equal to the sum of both of those individual gas pressures. So when we combine those gases, the sum will be 900 pascals, so the pressure of this combined gas will be 900. How do intermolecular forces determine states of matter? Intermolecular forces, or IMFs for short sometimes, are the forces of attraction between particles. So intramolecular forces are within a molecule, how the atoms are bonded together within a molecule, but intermolecular forces are between molecules. And we've discussed this in the past, but we're just going to go through this quickly again because it does affect the properties of the states of matter. The strength of the intermolecular forces helps to determine the states of matter and how easily a substance can change from one state to another. For example, methane here, molecules are only attracted by London dispersion forces, which are very weak. This causes methane to be vaporized at low temperatures. It is a gas at room temperature because of these weak intermolecular forces. So we'll talk about exactly what London dispersion forces means again, but just know here that it is a weak force, and so these molecules here are bonded together with a very weak attraction, and so they're able to separate from each other and therefore vaporize and spread into a gas very easily. These forces of attraction are not holding them together tightly, keeping them in a state of solid or liquid matter. So intermolecular forces have a great deal to do with the way that different types of matter react or interact with their environment. How strong are intermolecular forces? Well, we discussed here a second ago London dispersion forces, and these are the weakest because they are temporary forces of attraction between electron clouds in non-polar molecules. So again, methane is an example here. It is a non-polar molecule because of its symmetry. And so the bonds are pulling in opposite directions, causing an overall non-polar molecule. And so the only way that these molecules are actually attracted to each other is when the electrons move in the electron cloud and cause a very brief partial charge to one side of the molecule, and that induces a charge on the other side of the other molecule, and they're temporarily attracted to each other. Dipole-dipole interactions are a little bit stronger than London dispersion forces. This is an attraction between partial positive and negative charges on polar molecules. So ammonia, for example, is a polar molecule because it's asymmetrical, and so the hydrogen atoms are found down here. There are lone electrons up here, and that causes the molecule to have partially positive and partially negative sides. So the partially negative side would be this side that has lone electrons on it, and the partially positive side would be this hydrogen atom, and so the partially positive side of one molecule is attracted to the partially negative side of another molecule. And that's why we call them dipole-dipole interactions, because they are polar molecules that are inducing each other into an attractive state. Hydrogen bonding is an attraction between a hydrogen atom and a strongly electronegative atom. So here we have oxygen, which is a strongly electronegative atom, and hydrogen, and these form water molecules, which is an example of hydrogen bonding because one water molecule is attracted to another water molecule because this strongly electronegative atom of oxygen pulls on the electrons more strongly than the hydrogen atom. And so the hydrogen side becomes partially positive and the oxygen side becomes partially negative. And so the attraction between them is what causes lots of the properties of water, like surface tension, cohesion, and the fact that water takes a long time to vaporize. It requires a high temperature to vaporize because this attraction is very strong, and so they don't separate very easily. And so these intermolecular forces are ranked from top to bottom, from weak to strong. And in summary, pressure affects states of matter in different ways. Gases, for example, illustrate the cumulative pressure explained by Dalton's law. The strength of the intermolecular forces within a substance can determine how easily it changes from one state to another. How are particles arranged in solids? Solid substances have low kinetic energy, so low energy of motion. So the particles do not have the energy required to overcome the intermolecular forces. So these molecules are being held together by intermolecular forces, but they don't have the amount of energy required to break those bonds and release those particles into a liquid or a gas state. So this causes them to vibrate in place. Solids have a high density because the particles are closely packed together. Remember, these particles are not at rest unless they are at 0 Kelvin. So even though they're solid, they are still vibrating and moving. They just don't have enough motion to break themselves apart. Some solids, for example tar, are able to flow at an extremely slow rate, and these are known as amorphous solids. How are particles arranged in liquids? If the temperature increases and causes the kinetic energy to overcome the pull of intermolecular forces, the substance will melt and become a liquid. So as you can see, these liquid particles have more motion, more space between them because they were able to overcome some of those intermolecular forces. In a liquid, particles slide past each other because they are still loosely held together by some intermolecular forces. Because of the space between the particles, liquids are more compressible than solids, but less than gases. So pressure does affect liquids in a small way. It affects gases in a very large manner. What properties of a liquid can be explained by intermolecular forces? Well, I mentioned a couple of these. The strength of the intermolecular forces in a liquid can determine surface tension, the attraction of particles at the surface of a liquid. So you can see that these bonds between the particles here almost create sort of a film or a layer on that top surface, and that is called surface tension. And surface tension allows water striders to stand on the surface of a pond, for example, and that's because of these strong intermolecular forces between the water molecules, because they have that high attraction of hydrogen bonds. They're able to create that surface tension. Capillary action is another property based on intermolecular forces, and this is the ability of a liquid to be drawn up a thin solid tube. So you can see here the colored water is drawn up the celery stalk, and you can see the blue at the top here and the red at the top on this side, and that's due to capillary action. So there are tubes all through the celery stalk, and the water is attracted to the sides of the tubes in the stalk, which allows it to be pulled up the tube, and that's how plants are able to move water through their stems. And that's because the molecules of water here are attracted to each other And so if you can picture one water molecule being drawn up, it pulls others along with it because of those strong intermolecular forces. Third, viscosity is the resistance of a liquid to flow based on the attraction between its particles. So honey and syrup have high viscosities, and that causes them to pour slowly because the bonds are holding them together, and so it makes them seem thick. In summary, when kinetic energy overcomes intermolecular forces, the closely packed particles in a solid can move more freely, creating a liquid. Surface tension, capillary action, and viscosity can be caused by the intermolecular forces in liquids. What phase changes are caused by the addition of energy? So we're discussing phase changes now. Once a substance is able to overcome the intermolecular forces holding its molecules together, it is able to change phase. Matter can change from one state to another. This transformation is commonly known as a phase change. Energy is always involved in phase changes. The addition or removal of energy will cause matter to change states. So we interchangeably say here changing states or changing phases. And I'm sure that you are very familiar with phase changes from other courses in your science career. Here's an example. This ice cream is melting because thermal energy, otherwise known as heat, has been added to it. The thermal energy increases the kinetic energy of the ice cream particles, causing them to overcome some of their intermolecular forces and slide more freely in a liquid state. If they overcame all of their intermolecular forces, it would be a gas state. Adding energy causes melting, which is the change from solid to liquid, vaporization, which is from liquid to gas, and a type of vaporization here is evaporation, and that is vaporization specifically from the surface of a liquid. And finally, sublimation, which is the phase change from a solid directly into a gas with no liquid phase in between. Dry ice is an example of sublimation that occurs at room temperature. Solid carbon dioxide, so you might have a block of dry ice here, which is solid carbon dioxide, becomes vaporized without melting, which makes it good for shipping cold items because you can keep them cold without ending up with a bunch of liquid inside your box. What phase changes are caused by the removal of energy? Removing energy causes freezing, which is a change from liquid to solid, condensation, which is a change from gas to liquid, or deposition, which is a change from gas directly to solid. Here's an example. As the air moves very quickly over an airplane's wings, it causes it to cool and condenses the water vapor in the air, causing a small cloud to form. So you can see this cloud forming on top of the airplane's wings. And that's from the vapor in the air condensing into water droplets, which look to us like a cloud. Snow is an example of deposition because water vapor in the air changes directly into solid snowflakes. What is a phase diagram? Well, both pressure and temperature contribute to a substance's phase of matter. If you think about this a little bit, it'll make a lot of sense, I think. If there is greater pressure, which we discussed as force per unit area, then it's going to cause those particles to condense together and gravitate towards each other, bringing those closer to the solid state. Temperature is caused by the movement of molecules, and so the higher the temperature, the more the molecules are moving, and therefore the further apart they are and the closer to a vapor state. So pressure and temperature both can contribute to a substance's phase of matter. A phase diagram is a graph showing the phase in which a substance exists at varying temperatures and pressures. So each substance has its own phase diagram, although they look fairly similar. And you can see here at a specific temperature here, like negative 150 degrees Celsius, and any pressure, this substance is going to be a solid. So the temperature is so cold that the particles don't have enough kinetic energy, and so they're going to be in a solid state. A triple point represents the conditions at which all three phases can exist simultaneously. So here's the triple point on this graph. And the final point on here is a critical point. This is the temperature at which separate liquid and solid states cannot exist, regardless of temperature or pressure. So regardless of whether the temperature is increasing or decreasing, pressure is increasing or decreasing, these liquid and vapor states at the critical point and past the critical point become indistinguishable from each other. So they're really no longer separate states at that point. In summary, phase changes are caused by the addition or removal of energy. A graph showing the state of matter for a substance based on temperature and pressure is called a phase diagram. Let's focus now specifically on gases. Gases, as you know, have greater space between the particles, and so therefore they are more severely changed by variables such as pressure, temperature, and volume. And so we're going to look at how some of these variables specifically affect others in reference to gases. As a reminder, pressure is equal to the force per unit of area. So if you add particles of a gas to a container, they will hit the walls of the container more often. Because there are more particles in there, the container walls are going to be hit by the particles more frequently because there just are more particles inside it. Each particle collision against the wall of a container causes an increase in pressure because this is force. It's a very small force from those particles, but it is a force being pushed on the outside of the container, and that causes an increase in pressure. And so if you add a lot of particles, you're going to notice a change in the pressure of the container. A soccer ball, for example, that has gone flat can be filled with air. So we're increasing the quantity of air. We're adding particles of air, and that is adding volume, first of all, as well as changing the quantity of particles. And that air then pushes more on the outside of the ball, which causes greater pressure. So of course, blowing up a soccer ball is going to cause that soccer ball to have greater pressure on the outside, which is exactly why you refill it. In 1662, Robert Boyle discovered that doubling the pressure on a sample of gas, which was at a constant temperature, resulted in a reduction of volume by 1/2. So as we discuss some of these gas laws, keep in mind that everything is being held constant except for two variables. So pressure here is what's changing, or what he is specifically changing, and then he is measuring volume. So the quantity of the gas particles and the temperature of the gas particles is going to remain constant. So if we are doubling the pressure on a sample of gas, in other words, increasing it by twice as much, it is reducing the volume by 1/2. So that's being decreased by 2 times, and that is an inverse relationship. So as one is increasing, the other is decreasing. That's exactly the definition of an inverse relationship. The relationship is now known as Boyle's law, and it's written as P1V1 equals P2V2. In other words, the pressure at the beginning of the experiment and the volume at the beginning of the experiment, if we multiply the original pressure and the original volume, that is equal to P2 times V2, or the second resulting pressure times the second resulting volume. So these are what we start with. These are the result. And you can think of this as an equation just like you would write one in algebra class. And so we often rearrange these equations to solve for one of these variables. So we could figure out what the resulting pressure was going to be if we changed the volume from a certain amount to another amount. And we're going to do some problems calculating each of these variables. Here's a real-life scenario. A lava lamp contains a waxy substance and water. There's a light bulb at the base. So down here you have a light bulb, which generates heat. As the bulb heats the waxy substance, it rises. Near the top of the lamp, the waxy substance cools and falls. So they make these lava lamps just tall enough that the wax can cool at the top enough to then fall back down. And so it's sort of an ongoing cycle here. Turn and talk to a partner and discuss why you think this happens on a particle level. So if you're by yourself, you don't need to turn and talk to a partner. You can just think about this on your own. But so think about this on a particle level. What exactly is happening to those particles as they are down here by the lamp and they are gaining heat? What is happening to those particles? Pretend that you can see them. Think about what's going on here that's causing them to rise and fall. And here's our explanation. As the wax gets heated by the light bulb at the bottom here, the particles gain kinetic energy because we are adding thermal energy and it's being converted into kinetic energy, and the particles are therefore moving more, and that causes them to spread out. That makes the wax increase in size, which decreases its density. And so as this wax becomes less dense, it begins to rise in the liquid. As it gets to the top, it cools and it begins to condense, which increases its density, and therefore it sinks back down to the bottom. So you've, I'm sure, heard that hot air rises and cool air sinks, but it's important to understand what exactly is happening to those particles that's making them rise. They are adding kinetic energy from that heat and spreading out. So the wax is heating and expanding here and cooling and contracting at the top of that lava lamp. How are gas temperature and volume related? So we just discussed temperature. You should be able to visualize volume in this lava lamp example as we discuss the relationship here. Jacques Charles observed that when pressure and amount of gas are held constant, so we have two constants here, pressure and amount of gas, we are not making those variables, the temperature of a gas is directly related to its volume. So direct relationships mean that as you increase one variable, the other also increases. So the temperature of a gas is increasing, and that causes the volume as well to increase. Now, we're not discussing gases here, we're discussing wax, but same principle applies. As you are changing the temperature, increasing the temperature of the wax here, the volume is increasing because those particles have more energy and they are starting to spread out. So it makes sense that the volume is increasing. This discovery allowed him to derive what is now known as Charles' law. Volume 1 divided by temperature 1 equals volume 2 over temperature 2, or V1 over T1 equals V2 over T2 is how we commonly explain that. Again, this is the first or initial volume and the initial temperature, the resulting volume and the resulting temperature. So here's what this would look like in real life. If the volume of this cylinder was 600 milliliters, if we had 600 milliliters of gas in here, and the temperature was 300 Kelvin, the volume over temperature would be 2 milliliters per Kelvin. This should be a capital letter. Again, if we had a different situation here where our volume was 400 milliliters of gas and the temperature was 200 Kelvin, V2 over T2 would again be 2. And in a third situation, if we had 800 milliliters of a gas and our temperature was 400 Kelvin, V3 over T3, this is going to be a constant value. So whatever we are changing the volume by, the temperature is also changing, or the same, we could say the temperature is increasing by the same rate as the volume, giving us this constant value. So let's practice Boyle's law first, and then we'll practice Charles' law. A balloon has a volume of 3.5 liters of gas. The air pressure on the outside of the balloon is 1.0 atmospheres. What will happen to the pressure inside the balloon if it is placed underwater and the new volume is 1.25 liters? So Boyle's law here, we've got P1 V1 equals P2 V2. Our first pressure is 1.0 atmospheres. What will happen to the pressure? So that means that P2 is going to be our unknown. If it's placed underwater and the new volume becomes 1.25 liters. So our volume is changing from 3.5 liters to 1.25 liters. So V1 is 3.5. V2 is 1.25, and now we're going to plug those into the equation. P1 V1 equals P2 V2. Remember, these are multiplied together. So we have 1 atmosphere times 3.5 liters equals P2, our unknown, times 1.25 liters. And in order to solve this, we're going to divide both sides of this equation by 1.25 liters to get that P2 by itself. And our answer for P2 is going to be 2.8 atmospheres. So that's an example of a simple Boyle's law problem. And now we'll practice Charles' law. A sample of gas has a volume of 120 liters at a temperature of 40.0 degrees Celsius. The temperature drops to negative 10 degrees Celsius. If the pressure remains constant, what will be the new volume of the gas? So as we discussed before, anytime we're dealing with temperature of a gas, we're going to use Kelvin. So we know that our first volume is 120 liters. And we're saying if the pressure remains constant, what will be the new volume? So new volume here, or V2, is going to be our unknown. And we're going to convert these two temperatures into Kelvin. So it's starting at a temperature of 40.0 degrees Celsius. We're going to add 273 to get our 313 Kelvin for T1. The temperature is dropping to negative 10, so this is our T2. T2 equals negative 10 plus 273, gives us 263 Kelvin. Using the formula V1 over T1 equals V2 over T2, which is Charles' law, we can plug in all of our numbers. 120 liters over 313 Kelvin equals V2, our unknown, over 263 Kelvin. I find that the easiest way to solve these problems is to cross multiply. So you can cross multiply these two numbers here because you have both of those, and then divide by the outstanding number here, 313. So 120 times 263 divided by 313 gives you an answer of 100.83 liters. In summary, pressure, temperature, and volume of a gas are all related. Pressure and volume are inversely related, as shown in Boyle's law. Temperature and volume are directly related, as shown in Charles' law. And just as a reminder, inversely related means as one increases, the other decreases. And directly related means when one increases, the other also increases. What is Gay-Lussac's law? Gay-Lussac was a French scientist who focused on the relationship between gas temperature and pressure in the early 1800s. Gay-Lussac's law describes how the pressure of a gas tends to increase as the temperature of the gas increases, provided that the volume remains constant, which makes that a directly proportional relationship or a direct relationship. When the temperature increases, the pressure increases as well. And again, we're always holding volume, or we're holding one variable constant. In this situation, we're holding volume constant as well as the amount of gas in the container. So Gay-Lussac's law is written as P1 over T1 equals P2 over T2. And as you can see here, when we've got molecules moving slowly because their temperature is low and so they don't have a lot of kinetic energy, they don't exert a lot of pressure on the outside of their container. When they add energy through thermal energy or heat, the kinetic energy of the molecules increases and they bounce off the sides of the container, causing the pressure to increase. So the second flask has a higher pressure because the gas molecules have more kinetic energy. So let's practice. A 5.0 liter propane gas tank on a camping stove contains propane gas at a pressure of 2.0 atmospheres when the temperature is 14 degrees Celsius in the morning. During the day, the tank warms up to a temperature of 34 degrees Celsius. What is the pressure of the propane gas inside the tank during the day? So volume is remaining constant here. We're just talking about a propane gas tank, so we're not changing the volume throughout the day. It's just the temperature that's increasing. So T1, again, we are using gases, so we're going to use Kelvin for our temperature. So we're going to take T1, temperature in the morning of 14 degrees Celsius, add 273 to give us 287 Kelvin. Later in the day, so that's our T2, the temperature is going to be 34 degrees Celsius, add 273 gives us 307 Kelvin. And the pressure begins in the morning at 2.0 atmospheres, and we're looking for our unknown is P2. So we set up the equation for Gay-Lussac's law. 2 atmospheres over 287 Kelvin equals P2 over 307 Kelvin. Again, I recommend doing a cross multiplication here, 2 times 307, and then divide by your outlier. 287 Kelvin gives you an answer of 2.14 atmospheres of pressure. Can all the gas laws be combined? So we've discussed a lot of individual gas laws here, but they all deal with temperature, pressure, and volume. And since they're all related, the 3 gas laws can be combined into one gas law. And we call that the combined gas law. So if we put all of the Boyle's law, Charles' law, and Gay-Lussac's law together, we get P1 times V1 over T1 equals P2 times V2 over T2. And that helps us solve problems with a lot of variables more quickly than if we had to do it using the separate gas laws. So let's practice a question using the combined gas law. A weather balloon is filled at sea level with 8,000 liters of helium. The pressure at sea level is 1.0 atmospheres and the temperature is 17 degrees Celsius. Calculate the volume of the balloon at 25,000 feet when the atmospheric pressure has decreased to 0.4 atmospheres and the temperature is negative 35 degrees Celsius. So our atmospheres have changed here. That's pressure. Temperature has changed. And we are going to need to calculate then, we started with an initial volume, we need to calculate that second volume. So V2 is going to be our unknown. We are again changing these Celsius temperatures into Kelvin, and we're going to calculate for V2. Using the combined gas law, 1 atmosphere times 8,000 liters for volume divided by our initial temperature equals 0.4 atmospheres times V2 divided by 238. And you can cross multiply for this as well. You just need to come up with a total for the top of this fraction. So this is going to be 8,000 obviously times 238. Divide by the outlier here is going to be divide by 290. And then whatever that number is going to be equal to 0.4 times V2. So we just divide that number that we calculated by 0.4. And V2 should be then 16,413.79 liters. And this is not correct as far as sig figs, so that would need to be adjusted. But for now, let's focus on how we calculated the problem. In summary, Gay-Lussac's law compares the relationship between pressure and temperature. The combined gas law compares the relationships among all three variables of pressure, volume, and temperature. What is the ideal gas law? The ideal gas law incorporates the number of gas particles in moles with the combined gas law. So with the combined gas laws, we've been talking about pressure and volume and temperature of gases. We have not been focused on the number of particles or moles of the gas because that's something that we've been keeping constant so far. Since pressure and volume will both be affected when the number of gas particles is changed, because more gas particles means that the pressure will increase, there'll be more collisions with the walls of the container, and therefore the volume will increase because we're adding particles that will expand. Moles can be added into the equation like this. So if we put pressure and volume over moles, which is N here, and temperature, we end up with a constant value. And the reason this works is because if we use STP, for example, and we put in a standard pressure of 1 atmosphere and our standard STP volume is 22.4 liters, so we have 1 times 22.4 at the top, and 1 mole for N, and 273 Kelvin for our temperature. We always use Kelvin when we're dealing with gases. So we essentially have 22.4 over 273, and that value is a constant, which we call the ideal gas constant. And that shows us how pressure, volume, moles, and temperature are all related. The value of the ideal gas constant has been determined by doing many experiments. So lots of different values can be plugged in for lots of different gases here. We can change the pressure, we can change the volume, and all of those values, as they're changed, give the same constant value. And that's why we call it the ideal gas constant. So it's been determined by doing many experiments, and it's represented by the letter R and can have different values based on the pressure units used. The ideal gas law is written as PV equals nRT. So pressure times volume. Volume is going to be in liters. Pressure can change values. It's going to have different units depending on how the pressure in the problem is given to you. N is moles, R is the ideal gas constant, and then T is temperature in Kelvin, always in Kelvin since we're dealing with gases. The ideal gas constant is going to change. It can be one of these three values depending on what units the pressure is given in. So this is the most commonly used R value here. 0.082 liters atmosphere per mole Kelvin. And we keep these units exactly as they are. You're going to insert them into the problem using this whole value and all of these units as it is. And if the pressure is given in kilopascals, then we're going to use this R value. If the pressure is given in millimeters of mercury, then we'll use this R value. So the pressure and R value, ideal gas constant, will change or could change depending on how the units are given in the problem. So what are the conditions that we consider ideal in order for this ideal gas law to work? Well, the ideal gas law is just as it sounds. It's a hypothetical situation based on the assumptions of the kinetic molecular theory and that the gas particles take up no space. In reality, gas particles always take up a little bit of space, and intermolecular forces change the way that the particles interact with each other. So the way that gases behave in nature is not going to be exactly according to the ideal gas law, but it gives us a good reference point, and it allows us to calculate values that are pretty close to what would happen in nature. So let's practice using the ideal gas law. How many moles of hydrogen, H2, gas are contained in a volume of 2.0 liters at 280 Kelvin and 1.5 atmospheres? So we're going to set up our ideal gas law, PV equals nRT. Step 1, we're going to identify all of our variables here that we know, and our unknown here is going to be N because we're looking for how many moles. Step 2, isolate the unknown variable. So we're going to divide both sides of this equation by RT, because if we divide by RT here, we'll get N by itself, and that means that this side of the equation is going to be PV over RT. So now we have our rearranged equation, N equals PV over RT. And now we plug in our known variables from the problem, 1.5 atmospheres, 2.0 liters. We're going to use this R value, 0.082, because we have a unit here of atmospheres, and that is the unit that our pressure is given in from the problem. So atmospheres here matches the atmospheres in that R value. Notice that we're not changing these units at all. I am plugging it into the problem exactly as it's written. 0.082 liters times atmospheres over moles times Kelvin. So this whole R value is written this way all the time. I have some students that try to plug values in for these units here. That's not the way that you want to do it. We just keep the units exactly as they are, and we use the 0.082 value. And then we're going to multiply that by 280 Kelvin, divide, and we get 0.131 moles. And we should actually reduce that because the number of sig figs in the problem is 2. And so this should be 0.13 moles. And we're, again, always going to write the values for R here in our work for the calculations. Okay, another practice problem. Find the pressure of 3.40 moles of a gas if the gas temperature is 40 degrees Celsius and the gas volume is 22.7 liters. Remember, your first step is going to be to convert this into units that are usable in the ideal gas law. So PV equals nRT. Convert your temperature, plug your values in, and then come back and check and see if your answer matches mine. Okay, so we're looking for pressure. So let's find the pressure. Volume is going to be 22.7 liters. N is our moles. which is given here. And then temperature, we add 273 to come up with 313 Kelvin. And in order to isolate pressure by itself, on one side, we're going to divide both sides by volume. So we end up with nRT over V, gives us the pressure. And we're going to plug our values in here, 3.40 moles, 0.082 liter atmospheres per mole Kelvin. Again, this is our most common R value, and we're using this to come up with atmospheres. We could actually use any of the R values this time because our pressure was not given in the problem, what units were required. So we could give an answer here in atmospheres, or we could give it in kilopascals or so on, but we're going to use the most common. And 313 Kelvin plugged in for temperature divided by 22.7 liters gives us 3.84 atmospheres. In summary, the ideal gas law is an equation that combines the previous gas laws into one equation and incorporates the moles of gas particles involved. It is hypothetical, but can be used to estimate values for each variable.